So transmission line under electromagnetic theory, this is a quick revision. So this is propagation constant R, L, G, C are the primary constant of the line. It is alpha plus j beta, where alpha is the attenuation constant, unit is Newton per meter, and beta is phase constant, unit is radian per meter. The definition of beta is the phase change per unit length, and it is defined as 2 pi by lambda, where lambda is the wavelength of the wave on the transmission line. Now we have seen the unit of attenuation constant is Newton per meter, and this Newton is 1 Newton is 8.68 dB. Now the characteristic impedance, this is the formula for characteristic impedance, and ZL is the impedance seen at any point on the line, that is VL by IL, where VL is the voltage on the line and the IL is the current on the line. So these quantities are the superposition of the incident and reflected wave. They are not individual, they are superposition of both in incident and the reflected wave. The formula for ZL impedance at any point is Z0 1 plus gamma L by 1 minus gamma L. So the gamma L is defined as ZL minus Z0 by ZL plus Z0. This comes from this equation, and the gamma naught is the ZL, the impedance, load impedance, ZL minus Z0 by ZL plus Z0 is defined as the gamma L. Now this is the voltage and current equation at any location on the transmission line, and this is gamma L, V minus by V plus e to the power minus twice gamma L, and this is gamma L at load end. In general, this V minus and V plus has some phase, that is phi. So the overall gamma L is, this is the expression for overall gamma L at any location on the transmission line. Impedance transformation equation for lossless transmission line. So you have to remember this formula. The impedance over here is Z1, so Z1 comes here, and here is Z2, Z2 comes here and here. So how to remember this formula? So first of all, this cos function will be present at the beginning, and the sine function will be later. You can remember this by this way, that e to the power j theta is cos theta plus j sin theta. Similarly here cos theta is first and second sin theta is next. Similarly in here also cos theta first and second is the sin theta, where theta is beta L over here. And first here you have to write the Z2, because you are transforming this Z2 over Z1. So you can remember this way, that first you have to write Z2 and next Z0, Z0, Z2. Or after writing Z2, just remember the adjacent point should not be Z2, so they must be Z0, and that this point should be Z2, and here you should write the Z0. So this way you can remember this formula. Lossless transmission line, R equals to 0, Z equals to 0, and alpha is 0, and beta is omega root over LC, and Z0 is L by C. For lossless line, the characteristic impedance is real, that is, this is real. Now for a lossless line, the line is lossless, so there is practically no loss in the line, but the mathematical loss in the if you calculate the loss at any point mathematically, then that power loss, that is real power at any point on the line equals to the power delivered to the load. This point is very important to calculate the power delivered to the load by calculating the voltage maxima and the impedance at the maximum point, and you can calculate power dissipate at that particular point, and that will be equal to the power delivered to the load. For low loss line, R is very less than j omega L, and G is very less than j omega C, and the attenuation constant alpha is, so this is the formula. How to remember? The half is common in both case, and this is the RCL loop. Like in the network system, we know that RCL loop, that was basically tricks to remember the formula. This RCL loop here, and here also RCL loop in the reverse fashion. This G, you can think that this is G as 1 by R, so RCL, this is clockwise, this is anti-clockwise, RCL, 2 RCL loop. So this way you can remember this formula alpha, and beta is omega root over LC. Voltage standing wave ratio, mod of Vmax by mod of Vmin, and it is defined as a 1 plus mod gamma L by 1 minus mod gamma L. Here minus in the denominator, you can think it as that this voltage standing wave ratio could be 0 to infinity, so here it is minus, so that when this gamma L is 1, mod gamma L 1, then it could be infinity, so this here it has to be minus. Maximum voltage on the line is V plus mod of V plus into 1 plus mod gamma L, and minimum voltage mod of V plus into 1 minus mod gamma L. Maximum current is maximum voltage by Z naught, and minimum current is minimum voltage by Z naught. Impedance is maximum when the voltage is maximum, and when the voltage is maximum the current is minimum, according to this curve, this standing wave pattern. So the maximum impedance is Z naught into 1 plus mod gamma L by 1 minus mod gamma L. This is Z naught into rho. And similarly minimum impedance is Z naught by rho. So maximum impedance Z naught into rho and minimum impedance Z naught by rho. For the lossless line, this Z naught is real, so Z naught rho is also real, and for minimum impedance also the real quantity. So in the transmission line where the voltage is maximum, in that location the impedance is also maximum, that is rho Z naught, and the current is minimum. And similarly where the voltage is minimum, in that location the impedance is minimum, and so the voltage and impedance are in the proportion, and the current is maximum in that location where the voltage is minimum. Now impedance on a line repeats over every lambda by 2 distance, and the normalized impedance invert every lambda by 4 distance. Note here, for a load impedance Z is equal to Z naught, the impedance at any point of the line is Z naught. Power in the lossless transmission line, the complex power at any location on the line is given by, this is PL, and equals to half VL into IL conjugate, where it has a real part and it has an imaginary part. And the real part is the mathematical power loss at any point on the transmission line, and this equals to power transfer to the load. We have seen this in the earlier slide. And this is the imaginary power, this is the reactive power on the line. So the power delivered to the load is PL equals to half real part of this quantity at L equals to 0, and the formula is, you have to remember this formula, mod of V plus square by 2 Z naught into 1 minus gamma L square. Here 2 factor comes due to the RMS quantity, and V plus is the peak value. So this power delivered to the load has two parts. One is the incident power and another is reflected power. So difference between these two is the power delivered to the load. So this quantity is the incident power and this quantity is the reflected power. So in case of reflected power, you have to multiply by the mod gamma L square, and the difference between these two is the power delivered to the load. And we have seen that Z naught is real for lossless line. Should note here. Smith chart, here it is the impedance Smith chart. It is the complex reflection coefficient plane, that is gamma reflection coefficient is R, this length is R, and the phase is it toward J theta, this angle is theta. These are the constant resistance circles. Here the outer circle is the R equals to 0, smaller is 0, and this is R equals to 1, and here it is increasing up to infinity, and these are the fractions. And these are the constant reactance line. Here this is 0, x equals to 0, here this is positive, and here these are the negative, and here this is 1, x equals to 1, and here x equals to minus 1. Here it is integers increasing from 1 to infinity, and these are the fraction. Here also these are the fraction, and here it is 1 to infinity integers. The upper part denotes the inductive reactance, and this below part represent the capacitive reactance. As the x is negative, so it is capacitive reactance. So these are the constant VSWR circle. This is one, and this is another constant VSWR circle. How to draw it? First you mark the normalized impedance. Suppose normalized impedance over here, this point, this particular point. Now draw a circle with respect to this point, this origin, and this circle will be the your constant VSWR circle. Now to find out the VSWR, that is rho, first find out the intersection point of the constant VSWR circle with the x equals to 0, that is this line. So this is the point. Now calculate the value of r to this particular point. Here this value is 2, so the VSWR is 2 for this particular circle. So this VSWR could be from 1 to up to infinity. It could be any value depending upon the constant VSWR circle. Similarly for this circle, the VSWR is 5. Now define point on Smith chart. This is the short circuit point, and this is open circuit point, and this is matching point, impedance matched. If your normalized impedance lies here, that means your transmission line is matched with the load impedance. At this open circuit point, the reflection coefficient gamma is 1, and in the short circuit point the reflection coefficient is -1. Here the reflection coefficient gamma is j, and here is reflection coefficient gamma is -j. In this two case, the reflected or the gamma value, the mod of gamma value is 1 in this two case, but the phase is in one case is 90 degree and in this case is -90 degree. This means at the load end, the reflected wave and the incident wave, and there is a 90 degree phase shift plus minus, that is plus 90 degree or the -90 degree, the phase difference between the incident and the reflected wave. So these are the different point in the Smith chart, that is the impedance Smith chart. Now suppose this is a typical ZL normalized impedance, and you draw the constant VSWR circle. So this point is for voltage minima, right, and this is for current maxima and the impedance minima, and this point is for voltage maxima and also current minima and impedance maxima. How to remember? Note that in this side the R value is greater than equals to 1. So the impedance, you can think the impedance is the more than equals to 1. That's why the it in this side it will be the maximum impedance, and the impedance is maximum means the voltage is maximum, and the voltage is maximum, at that point the current is minimum. And similarly in this side the R value is a fraction, so you can think that in this side the impedance will be minimum and the voltage is minimum, because the impedance is minimum, and so the current is maximum in this side. Now this is one standing wave pattern generated in the CRO, and this are another standing wave pattern. By looking at the standing wave pattern, you can decide whether the load is inductive, capacitive, or complex inductive, complex capacitive, or purely resistive. You can decide by looking at the standing wave pattern. So let us see how to decide. Suppose this is a particular point, there is a normalized impedance, and in that case what you encounter first? You will encounter first a voltage maxima, right? So if you find that a voltage maxima at a distance L0 from the load, then you can conclude that it must be a inductive load, because the upper half, this side, is belongs to the inductive impedance. Now whether it is a complex inductive impedance or the pure inductive impedance, that will depend on the minimum voltage. If this minimum voltage is 0, then it means it is a pure inductive impedance. That means this case here the minimum value is 0. This is because if your R is 0, then your belongs to this smaller equals 0, this outer circle, the constant VSWR circle. This is this outer circle. In that case your minimum voltage will be here, and this is belongs to 0 voltage, right? And one should note that this V minimum equals to 0, it is the ideal case, and you cannot find the load where the R is 0, so you should remember this thing. Similarly, you can decide whether the other loads are inductive, capacitive, or anything else. You can decide the same way. Note here, for the pure resistive load, you are either in this point or in this point, right? So if you are here, you will get the voltage maxima. That means this case where R is greater than equals to Z0. Because we have already said that here the R value is large, impedance is more, so here R is greater than Z0. And if you find the voltage is minimum, that means here, and in that case your R value is less than Z0, and here is the voltage minimum, means this dotted line, this case. So this way you can identify the others. Now let us see one example on the impedance Smith chart. Suppose ZL load impedance, this is the load impedance, and the Z0 is the characteristic impedance of the line. So the normalized impedance is 0.5 plus J 0.7. So 0.5 line. So this is the 0.5 line. Suppose this particular line is 0.5 line, R equals to 0.5, and this line is X is 0.7. So this is the point, intersection point. So you draw a line to this point, from this point to this point, okay, and this length R is called the modulus of reflection coefficient at load point, load line, right? And this angle theta is the angle of the reflection coefficient. So you can draw the constant VSWR circle. You can calculate the rho VSWR from here. If you want to calculate the admittance, you just extend this line over this side, and the intersection point with this constant VSWR circle is the normalized admittance YL bar. So if you want to find the impedance at any location L from the load end towards the generator, then you have to rotate this in this clockwise direction up to a length L, and you can find the impedance, normalized impedance at that location, and the corresponding phase with respect to this U plus JV axis, and that is the impedance and corresponding phase at that location. And one should note that total this 360 degree rotation is the length of lambda by 2 distance, this total 360 degree rotation. Now we will see how to use this admittance Smith chart from the impedance Smith chart. So this is the impedance Smith chart. You just have to change the axis. Suppose this is our U axis and this is our JV axis. In the previous case, our U axis over here, it was over here, and sorry, U axis over here and the JV axis over here. In this case, the U axis here and JV axis over here. Now rules are same for admittance Smith chart as for the impedance Smith chart. The upper side is a positive JB and lower side is minus JB, and the R circle is equivalent to the G circle, the conductance circles, and B circles are called the susceptance circles. Now in the impedance Smith chart, the upper side was the inductive type, and in this case the upper side is the capacitive load and the below side is the inductive load. This point was the short circuit point in the impedance Smith chart, but here it is open circuit point, and this is the short circuit point. It must be, sorry, it is not open circuit, this is the short circuit point, right, in the admittance Smith chart. So all the calculations are same as the impedance Smith chart, but one except one problem, that is the calculation of the phase. You have to calculate the phase with respect to this U plus JV axis. So let us see this particular problem with the example. So this is the admittance Smith chart example. Suppose YL is this on the YL, and we have to calculate the gamma Y and at 0.12 lambda from the load. So it is basically YL bar, and here is a mistake, YL bar, it should be YL bar. So YL bar is 0.2 minus J 0.5. So this is the YL bar, and this distance is 0.12 lambda by 2 lambda 0.12 lambda, this distance. So you can calculate Y bar over here, and it must be Y bar, so it is 0.18 plus J 0.28. And by a scale you can calculate this length R is 0.706, and this length is the reflection coefficient gamma, and the angle, so the angle you have to measure the angle this way, this side. So the angle is 328 degree, so this is 0.706 328 degree. Similarly, you can calculate the impedance by extending this line over this side. So this is Z bar, and the Z bar is 1.6 minus J 2.6, and the angle is 301.6 degree. So the angle has to be measured this way, this is the angle, and the rest of the calculation is same as the impedance Smith chart, only you have to calculate the phase from this axis, right? Now the application of transmission line is that to identify the unknown load with the help of the standing wave pattern. So you can get the standing wave pattern, this standing wave pattern in the CRO by the experimental kit. So we have seen for different type of load this pattern will be different, and the location of this maxima minima will be different for different type of load. So you can calculate this rho from the Vmax and Vmin. This is Vmax, Vmin, the standing VSWR, and similar from that you can calculate the Rmax, Rmin, right? So these are the location of Rmax, so the maximum voltage is maximum in that location, R is maximum, or the voltage minimum, the R is minimum, or the impedance is minimum, and it is real here because our assumption is that the line is lossless. And by applying the impedance transformation relationship, you can calculate the specific load impedance with this length L minimum. Now transmission line as a circuit element, so this is short circuit element. In that case, Zin is JZ0 tan of beta LSC, this length. And for the open circuit length, transmission line, this is Zin is minus of JZ0 cot of beta L. So with tan beta L there is no -1, with cot beta L there is -1. So the next application is the impedance matching using the quarter wave transformer, and it is used to match two real impedance and if your load is not real, then the section of transmission line can be used to convert the complex load into a real load. Suppose you have a complex load and you use the transmission line, so that after transformation of the load impedance, it's become a real impedance, right? After that you can attach that particular section of line over here, and here you have the another transmission line. Suppose you can match these two transmission line by this quarter wave transformer. When you attach a particular transmission line on this in this side, in that case it will offer the characteristic impedance of the particular this transmission line on this side, and we have for the lossless transmission line it is real, so you can attach this particular transmission line over here in by replacing this RB. You have to attach over here, and in this side you can attach the load with the help of a section of transmission line. So one thing you should know, that a long distance transmission line offer input impedance same as the characteristic impedance. If you have the very long distance of line, then its input impedance is the characteristic impedance. Now stub matching. You can solve many problem. Then this type of will be very easy to solve when you practice more and more problem. And suppose this is a particular stub, you have attached this particular stub over here, and suppose here is another load. Its transform impedance over here will be here, its transform impedance, and there is a parallel connection. You have to add this to admittance. You just calculate the admittance, and for this load and for this stub you just have to add this admittance. So this way you have to solve this stub matching problem. And next is the lossy transmission line. And lossy transmission line, Z0 is root over R by G, because you can neglect this two part, because R and G is very large, and gamma is similar root over RG. You can neglect this two part. In this case beta is 0, so there is no wave nature. So gamma is basically alpha, it is the attenuation constant. Now characteristic impedance for the coaxial cable, it is Z0 is 138 by root K. K is the epsilon R, that is the relative permittivity, and this is log of D1 by D2, and here this is Z0 is 276 by root K. The root K is common both the case, and this is log of D, this capital D by small r. Note that this in both the cases, this ratio, the D by R and D1 by D2 both are greater than 1. See here, D2 by D1 D1 by D2, and here is capital D by small r. For coaxial cable we have taken two diameters, and in the this parallel wire transmission line we have taken one diameter divided by, or this is not diameter, this is the distance between those two line, and the radius r, and the distance is d with respect to the center of the conductor. So distortionless line, the definition is that the distortionless line is one in which the attenuation constant alpha is frequency independent, while the phase constant is linearly dependent on frequency. So the condition is that RC equals to LG. How to remember? Here RC is the time constant of a RC circuit, or LG the LGTV. This way you can remember RC equals to LG. And the gamma, propagation constant gamma, this is the expression for gamma, general expression, and for this distortionless line it is root over RG 1 plus J omega C by G. And you have to remember this alpha and beta value. Alpha is root over RG, and beta is J omega root over LC. Beta is same for other line like lossless line and low loss line. Now the S parameter. So you have a high frequency two port network, and A1 is the incident RMS value of the incident wave, and B1 is the RMS value of the reflected wave at port 1. Here we have shown that B1 in this line, it doesn't mean that A1 is going through this line and B1 is coming through this line. It means that B1 is reflected from port 2. Like it's a voltage, it is appearing over here, the reflected voltage, right? You can also show here the B2, right, in the opposite direction of A1. Similarly A2 is the incident voltage, incident RMS value of the incident wave at port 2, and B2 is the RMS value of the reflected wave at port 2. So our S parameter matrix equation, this is the B1 B2 is S parameter matrix A1 A2. So here it is a reflected voltage quantities, and here is the incident voltage quantities, and this is the equation. In this two-port network parameter, here B1 and B2 is the function of A1 and A2. That means reflected voltage as a function of incident voltage, and the parameter are these are the parameter S11, S12, S21, S22. Here Sij, where J is represented the output port and I is represented the J is represented the input port and I is represented the output port. Now in this all these four parameter, you always find this way, this B by A ratio, always B by A ratio, and the B1 here, one is come from here and this one come from here, and here this two from here and this one from here. Similarly for other these two cases, and A2 equals to 0, A1 equals to 0, these are the condition. Now we will see how to make this A2 is 0 and A1 is 0. Now we have this high frequency two-port network. Here these lines are the transmission line. This is the transmission line, this is the transmission line. The characteristic impedance is Z2, and characteristic impedance on this side is Z1, means this side the characteristic impedance is Z1, and in this side it is Z2. Now to make this A2 0, that means there will be no reflected wave from this side. So what you have to do, you have to terminate this side with the characteristic impedance of this transmission line, that is Z2. Similarly, to make A1 is 0, so you have to terminate this port by Z1, because the characteristic impedance of this transmission line is Z1. So this way you can make A1 and A2 0. Now S11 means the input reflection coefficient, that is gamma in. So it is the ratio of the RMS value of the reflected voltage to the RMS value of the input the incident voltage, with the condition A2 is 0, means you have to terminate by Z2 over here. Now S21, it is the forward gain or the insertion loss from port 1 to port 2. So B2 is here, this is B2, and A1 is here, this is A1. So B2 by A1, this is the gain, the forward gain, with A2 is 0. So here A2 is 0 by terminating this port by Z2. Now S12, it is B1 by B2, it is the reverse gain or the insertion loss from port 2 to port 1. This is port 2, this is port 1. So this is B1 by A2, right, by making A1 is 0. So terminate this port by Z1, then A1 is 0. Now S22 is B2 by A2, it is the output reflection coefficient at output port, and with the condition A1 is 0. So A1 is 0 by terminating this port by Z1. So let us see one example. In this problem, find the S parameter matrix for the given network. So this is the network. Here is one transmission line, here is one transmission line, and this is in the network, and the characteristic impedance Z01, here is Z02. Okay, so to find S11, this is B1 by A1. First we have to make A2 is 0. So to make A2 is 0, terminate this port by 50 ohm, because the characteristic impedance of this transmission line is 50 ohms. But in this case, our this transmission line, that is Z01, this transmission line is perfect match with this load R equals to 50 ohm. So there is no reflected wave independent of this, whether you connect this one or not, but there is no reflected wave because of matching condition. So the reflection coefficient is 0. Similarly for S22, in this case also, this side, this transmission line is matched with this resistance R, so there is no reflection. In this case also, the reflection coefficient of the output port is 0. Now S12, what is S12? This is B1 by A2. So B1 is the reflected wave in port 1, so this is the reflected wave from port 1, and A2 is the incident wave at port 2. So it is clear from this circuit that this A2 is equals to B1. That means the voltage over here, the RMS value of the voltage over here, this B1 is equals to A2, and we have it is because we have made this A1 equals to 0. This A1 means here the A1 incident wave at port 1 is 0, because we have matched this transmission line by the 50 ohms load here, so that the whatever B1 is coming here, it is not reflected back. So A1 is 0, whatever incident wave, A1 is 0. So B1 is A2, so S12 is 1. Similarly, in the same way, you can calculate this S21. which is also 1, because of the you have matched these 50 ohms with this transmission line. There is no reflected wave from this 50 ohms load, so A1 is B2, so S21 is 1. So for the given network, this is the S parameter matrix. So 0 1 1 0, this is the S parameter matrix. Thank you.